Hello, my name is Ehsan. Thank you very much to have me in your journal club and giving me the opportunity to present my work here. In past couple of years, I have been working on Cosmicflows-4 program, and I was trying to measure the distances of more galaxies to advance these type of catalogs. I have been working with Byronic Tully-Fisher, Deep Anand, Alexandra Dupont, and the other people in the Cosmic Flows program. Basically, in Cosmic Flows, the main objective is to measure the distances of the galaxies in the local universe with the goal of measuring their peculiar velocities. So as long as we have the radial velocity of the galaxies, Hubble constant, and the distance of the galaxy, we can measure the peculiar velocity, which is basically is the deviation of the galaxy velocity from the Hubble expansion rate. Once we have the peculiar velocity, we can apply some cosmological models and simulations to figure out the underlying mass distribution of the galaxies in the area that we have data for, or we can construct the velocity fields. And so Cosmic Flows started in 2008 and a little bit earlier than that with 1800 galaxies within 3000 kilometer per second, and further advanced to Cosmic Flows 2 in 2013 with 8000 galaxies within 15,000 kilometer per second. Cosmic Flows 3 was actually the augmented Cosmic Flows 2 with distances of galaxies from 60F survey that were measured based on fundamental plane relationship of elliptical galaxies. Anyway, Cosmic Flows 3 ended up with 18,000 galaxies within 15,000 km per second, basically the same velocity coverage as Cosmic Flows 2. And in Cosmic Flows 4, we are trying to measure even the distances of more galaxies and uh, change the size of the catalog basically by the factor of 2 or 3. But the velocity range is basically the same. So basically what we are doing here in Cosmic Flows 4, and that's basically similar to whatever we had in previous versions. We are taking different methods of distance measurements like Tully-Fisher distance method, fundamental plane distance method, that work for spiral and elliptical galaxies, and the accuracy is like 20-25%, which is not very good. But if you are grouping all of these galaxies together, if galaxies reside in a group, you can just average out the distances of these galaxies and get better signal, velocity signal, if you are looking for velocities, for example. Or we have surface brightness fluctuation methods where you look at the fluctuations of the surface brightness of elliptical galaxies, large elliptical galaxies, and based on that fluctuation, you are able to measure the distance with the accuracy of 5%. And also supernova type 1a as a standard candle, the accuracy is between 1 to 5%. And tip of red giant branch method that gives you distance with the accuracy of 5 to 10%. But the only problem with TRGB is that it's not a problem, it's an issue, more or less. It only works within very local region of the universe, like less for distances less than 15 megaparsecs. What we are doing here, we are assuming that all of these distance catalogs are free of any internal bias, and they are only different in terms of their 0 points because they basically don't have any 0 point. We try to just put them on the same 0 point, and for that we just assume that one of these catalogs that we are trying to combine has the base 0 point, and for finding the relative 0 point of the other galaxy catalogs, we just look at individual galaxies and we use this kind of, for each individual galaxy, we use this kind of Gaussian likelihood function, where dns is the distance modulus of the object n in sample s, and this is the average of all of the distances of object n in different samples. And basically in this Bayesian framework, we try to sample all of these relative 0 points and find the 0 points that we should, based on which we should combine these galaxy catalogs. We have 12,000 galaxies with Tully-Fisher distance measurements, and these are different methodologies of Tully-Fisher distance, different catalogs of Tully-Fisher distances. And CF4 has like an additional 10,000 galaxy distances, and the redshift of these galaxies are not going beyond 20,000 kilometer per second, and they are well within 15,000 kilometer per second. And the redshift distribution of CF4, or the additions to the CF3, is kind of the same as the previous versions. And here you see the supergalactic ATOF projection of these TF distances. Here, this is, for example, Virgo cluster, Virgo southern extension, and the other regions. Also here we have fundamental plane targets, and Cosmicflows-4 benefits from the fundamental plane measurements that are based on SDSS images, and we have an addition of 30,000 galaxies in Cosmicflows-4, and this is the distribution of these galaxies. As you see, many of these galaxies are residing very far away than the rest of the sample. But the good thing about this catalog and the previous catalog is that they are mainly covering, because they are using SDSS data, they are mainly covering the north sky, where we lack or we were missing some information on galaxy velocities in Cosmicflows-3. So Cosmicflows-3 basically covers the southern sky, and that helped us to understand many things about the southern sky structures. But Cosmicflows-4 is supposed to have more galaxies in the northern sky, and that gives us a chance to learn more about the north, or the structures that we didn't have many data points for. Here I am plotting supernova type 1a distances that we have. The distribution of the galaxies are not that different. We ended up with 800 galaxies in our supernova sample, and SPF also is a harder method for distance measurement, and we don't have many galaxies in our SPF sample. We have only 500. I don't have TRGB here, but TRGB has only another like 800 galaxies, and when we add all of these galaxies to each other, we end up with 50,000 galaxies in our Cosmicflows-4 sample. But because our Tully-Fisher distances is not that finalized, we are still waiting for that catalog to be finalized and published. Once it's published, the rest is easy. We combine all of these distances with each other, and then we ground them based on other methodologies like parallax or TRGB or the Cepheids period luminosity relationship to just have a solid 0 point. As soon as we have we combine all of these distances and we have a solid 0 point for all of these distances, we can just publish that, and we can say, okay, this is our Cosmicflows-4 distance catalog, and based on that we can do other analyses, cosmic flows analysis, like deriving the mass distribution or the structures of the covering regions. Here I am going to concentrate or focus on TF distances and the method we used to measure the distances. The catalog that I worked on for distance measurements consists of 10,000 galaxies, mainly, as I mentioned earlier, they are mainly uh, distributed in the north sky. This is the galactic plane, and the green light here, green color, shows the cosmic 3 distribution of galaxies, and red shows the TF distances of Cosmicflows-4, and as you see, it's covering the area that we didn't have many distances before. So basically, TF relationships works as follows. We know that the luminosity or the mass of galaxies is proportional to the velocity to the power of 4 or 3. If you take the logarithm of both sides, luminosity becomes absolute magnitude, and here we have logarithm of velocity. But in order to measure velocity, we need to have a proxy, and our proxy here is helium atomic hydrogen molecules, atomic hydrogen clouds, which are emitting at 21 centimeter. And what we observe here is basically the velocity, rotation velocity of these spiral galaxies that is kind of projected on the plane of observation. And what we are doing here, what's happening here basically is that because these galaxies are spiral galaxies, are still going through the star formation process, they have a lot of atomic hydrogen clouds that are rotating with the galaxy. Atomic hydrogen has one electron and proton, and they have two states. One is when both of these spins are at the same direction, and the other one is when the spins are at opposite directions, and they emit a photon at 21 centimeter. And this process happens spontaneously. So, and as the clouds are rotating with the galaxies, some part of the galaxies are moving away from the observer, and some parts of the galaxies are moving towards the observer, and that causes that emission broadened. And by measuring that broadening factor, you can measure how fast the galaxy is rotating. Another factor that is important is the inclination of the galaxy, because if the galaxy that you are looking at is totally face on, you won't observe any broadening, because you can't observe the rotation of the galaxy. If the galaxy is totally edge on, you can still observe the rotation of the galaxy. So before using that relationship, the correlation between luminosity and line widths of the galaxies, spiral galaxies, we need to calibrate somehow this relationship. So that relationship basically is a linear relationship between the absolute magnitude of the spiral galaxies and the logarithm of the rotation velocity, which is then proportional to the logarithm of the inclination corrected h1 21 centimeter line widths. And that linear relationship can be represented by a slope and a 0 point. And as soon as you calibrate the relationship and you have these two parameters, you can just give for a galaxy with the given line width and inclination, you can measure the absolute magnitude of the galaxy, and then you can measure, based on the apparent magnitude of the galaxy, you can measure the distances to these galaxies. So to do that process, we need many pieces of information. One of them is basically the H1 line widths, And here I'm gonna thank to Ellen Corto, Alexander Dupoy, and the other people who worked on H1 observations of the local galaxies, spiral galaxies. And also we need to have photometry data. Basically, we need to know the apparent magnitude of these galaxies, and for that, we are using multiple ground-based or space-based telescopes. Our H121 centimeter profiles come from different telescopes, radio telescopes, Parkes, Nancy, GBT, Greenbank, and Arecibo. And the main contribution also comes from Arecibo, that recently, like a couple years ago, they published their uh, full sample of their survey, and I am showing their survey here in blue, and the footprint of the SDSS survey is in red. And they designed their survey to have the maximum overlap with SDSS imaging area. So therefore, we can use wherever we have H1 data, we can use SDSS images basically in order to do photometry. So the main contribution for cosmic flows for H1 data comes from alfalfa survey. And the photometry data comes from SDSS and VICE. So basically, initially, uh, we have been trying to use Pan-STARRS imaging survey for the photometry purpose, but that data didn't have very good quality. Then we switched to SDSS because they have better quality and they have coverage at different bands, like 5 different bands, U, G, R, I, Z. And also we have voice data. We used voice data wherever we don't have SDSS coverage, because we have many galaxies still that are located in the south where we don't have SDSS coverage. But basically, you can use whatever good imaging information that you have for photometry, but the only thing is that for each wave band, you need to calibrate the Tully-Fisher relationship. So here uh, I am showing the equatorial ATOF projection of all of these galaxies that I've included, and I am using these galaxies. I am basically trying to find the distances of these galaxies based on TF relationship. For many of these galaxies, like for 5,000 of these galaxies, I have just SDSS coverage. For 2,000 of them, I have SDSS and WISE. For 3,000 of them, I have only WISE coverage. And basically, those galaxies are located in the south. And also, WISE covers the entire sky. We could have potentially covered the entire sky using the WISE photometry, and we could add WISE to these area as well. But the WISE photometry is kind of harder for us, and we didn't have a lot of time to just finish the entire all the photometries using WISE data. Therefore, whenever we had access to SDSS, we just used SDSS. And the photometry process was kind of challenging because we needed to mask the foreground stars or the companion galaxies or any anomalies in the image. And just basically, we developed something like Photoshop to facilitate this process. We trained like uh, 10, 15 undergraduate students and friends to help us with the photometry process. It took us a year to go through the entire sample of like 20,000 galaxies that we originally had. Many of these sample galaxies have been rejected, but it took us like a year to complete the photometry. And basically, what they've been doing, they have been changing the aperture size, the annulus size, or the number of masks they put on the galaxy image, or they needed to just go backward and forward to just make sure that these growth curves or surface brightness uh, profiles look good and acceptable. So that was the reason that we paid so much attention to details to make sure that we have very good photometry, because if we don't have good photometry in the end, the distances that we measure, they are not acceptable at all, or they don't have good quality. Another issue that we had, I said that we were trying to use pan stars, but pan stars images are not very good in quality, because they are very very good in terms of the point source object photometries, but when it comes to extended objects like galaxies, they are not doing a good job. Like you see the footprint of the chip that they have been using for covering the sky, and you see the footprints, and the sky background subtraction hasn't been done correctly. So the photometry results of pan stars data for the extended objects didn't look promising, so therefore we used SDSS, which gives us very good data. And also, if you use pan stars information, you have to put a lot of masks, and it takes forever to go through all the images that we have. Another pieces Another piece of information that we need for this kind of process is the inclination of the galaxies. So if the inclination of the galaxy, if the inclination of a galaxy is zero, it means that the galaxy is face on, like this galaxy. If the inclination is 90 degrees, it means that the galaxy is totally edge on, and anything between these two values means that the galaxy is ranging between face on to edge on. So one of the ways that we can measure the inclination of the galaxies is to look at the axial ratio of the projected ellipse that we use for photometry, but that ellipse doesn't look very good when it comes to edge-on galaxies with very big bulges. So if the bulge of the galaxy is large, you see that the light of the galaxy is kind of the aperture that you use for the photometry is kind of elliptical, and the ellipticity is kind of large, but we know that the galaxy is actually edge on. For example, this galaxy M104, if you use the aperture that we use for photometry, you end up with a circular aperture, and you report that this galaxy is totally face on, but we know that the galaxy is edge on because we see the disk of the galaxy. So that relationship, which converts the axial ratio of the galaxy aperture to inclination, doesn't work, does only a good job in 30% of the cases, and for the other cases we need to be careful. And also I'm gonna add that if you don't do a good job in terms of measuring the inclination of the galaxies, the distance that you measure in the end is totally garbage. To do that, we came up with another solution, which was originally uh, uh, proposed by Ellen and her collaborators, to just come up with to just compare the target galaxy with a set of standard galaxies with known inclinations. So we designed this graphical user interface that allows like astronomers, amateur astronomers, or citizen scientists to just log in and work with the galaxies. They have a chance to just move galaxies right and left and compare them with the other galaxies. They can zoom in, zoom out, rotate these galaxies to make sure that they are doing a good job. And this way we make sure that we never make mistakes in measuring the inclination of the galaxy. So like we put 13 hours of work with the collaboration of like 15 undergraduate students and amateur astronomers, like 10, 15 amateur astronomers, to finish the job. And we required each galaxy to be at least 3 times measured by 3 different users to make sure that uh, we have enough data points to average and have a good measurement of the inclination of these galaxies. Also, we asked users during the process to report any bad galaxy or disturbed galaxy if they see any tail or trail or any kind of ambiguity in the galaxy. If a galaxy is not a spiral, they had a chance to um, report that, because we initially, when we selected our sample, we just roughly selected our sample and we didn't have much information about individual galaxies. Also, during that process, some of these cases popped out, like this case that when we did the photometry process, we didn't observe that galaxy, we didn't see that galaxy in front of this galaxy, or these two are interacting with each other. But apparently, when you look at the um, measured H121 centimeter line width, you see that there is a galaxy or there is some anomaly going on here, and we immediately dropped that galaxy from our sample and we rejected it. And also, there are many other cases, like these 6 cases where galaxies are interacting with each other. So, as soon as a galaxy is interacting with another system, the dynamics of the galaxy is disturbed and the Tully-Fisher relationship is no longer uh, true. So the averaging process of the inclinations helps us to have better inclination measurements, more accurate inclination measurements. But in order to quantify the measurements of the users, I divided these users in 2 different group A and group B, on average the inclinations of the common galaxies, and I compared the results with each other. Uh, the black line here shows the equity line. The blue dotted line and red dashed line shows plus minus 5 and plus minus 10 degrees difference. And when you compare the results, you see that after taking the average or taking the median value, your RMS accuracy is about 2.7 degrees. Also, there is another thing that's going on usually when you average all the inclinations for galaxies and you compare the results of an individual user, you figure that some of these users make a lot of mistakes when they measuring inclinations. They tend to report larger inclinations or smaller inclinations based on whatever they've been training on. Therefore, we need to come up with some iterative process to just modify their measurements in order to improve the accuracy. In the end, when you compare the individual measurements with the inclinations that come from the median values for all different galaxies, you notice that for very, very high inclinations or very edge on galaxies, the mistakes are smaller on average, like the scatter of the mistakes is smaller. Like at 90 degrees, we make mistakes of 1 degree, but at lower inclinations, when galaxies become more and more face on, the mistakes are larger and it just rises to 6 degrees, 5 degrees, something like that. Here, uh, here is the distribution of the inclinations in our sample. Like the inclinations, we have more uh, highly inclined galaxies, more edge-on galaxies than face-on galaxies. And this is a good news because whenever a galaxy is edge-on, any mistake in the measurements of inclination doesn't affect the measurements of the distance. Also, I should mention that 25% of our original sample has been rejected due to various reasons, like the reasons that I mentioned earlier. And in the end, out of 20,000 galaxies that I started with, I'm left with 10,000 galaxies for distance measurements. So for calibrating the Tully-Fisher relationship, basically we don't have the absolute magnitude of the galaxies. In order to get the absolute magnitude of the galaxies, first we need to calibrate these relationships. So uh, the way to do one of the ways to do that is to look at the galaxies that reside in a group, like the galaxies inside the Virgo cluster. We know that these galaxies are more or less at the same distance. At least when you look at these diagrams, they are at the same distance. And instead of using absolute magnitude, here I can use the apparent magnitude of the galaxies that I have measured. And I have the line widths of these galaxies, and we can construct a linear relationship. But this linear relationship is in apparent magnitude space, and uh, the slope of that relationship is not the same for all the clusters. Like if you look at Virgo, Cancer, Coma at different distances, you see that the slope might be different. In order to improve the statistics, we just measured the 0 point of these lines. We move all of these lines to a same distance, like to the distance of the Virgo cluster, and we form a universal template here. We fit a line, then we go back. Based on the fitted line, uh, we find this new 0 points, and we move all the galaxies to the same location, and we move back and forth until the algorithm converges, and we end up with a good slope calibration. Once we are done with the slope calibration, we just use the same slope with a set of galaxies with known distances, like their distances coming from TRGB or Cepheids methods. Then we use that slope to get the 0 point, and basically we ground the relationship. Once we have 0 point and a slope, our relationship has been totally calibrated and we are good to go. We can use that relationship to measure distances. Here, what I am showing you here is all of these clusters that we've used: Virgo, Ursa Major, Pegasus, Coma, and the other galaxies in different colors. They are all moved to the distance of the Virgo cluster, and this is the 0 point difference between Virgo and Ursa Major, for example, and the other clusters as well. And here I'm showing all the 0 point calibrator galaxies in black. Based on these galaxies, I've measured the 0 point of the observation. And you do that for all different bands, like G, R, I, Z, W1 and W2, and for each band you use the corresponding relationship to measure their distances. In the end, the scatter of these points about the fitted line is important, because we witness a scatter of like 0.4 magnitude, which corresponds to the accuracy of the measured distance of about 20%. It means that a scatter of 0.4 magnitude is translated to the accuracy of 20%. And if we can find any other way to improve that scatter, we can improve the accuracy of the measurements. And once you have measured all of these distances, you can do a bunch of calculations, like basic calculations. You can measure the Hubble constant, and plot it against the redshift, and we ended up with a value of 75 kilometer per second per megaparsec. But this is not the total story, because that parameter, that Hubble constant, is kind of coming from these galaxies that I used here. If I change my sample here, if I use any other sample that gives me another Hubble constant, it means that in the end I end up with another Hubble constant here. So basically that Hubble constant is kind of related to whatever I use for 0 point calibration. But the main import, our point here is not measuring the Hubble constant. Hubble constant is a byproduct of our calculation. The main point here is to uh, make measurements without any bias. So we don't want to have any sort of bias in our sample. Like we don't want to have some sort of bias like the bias that I'm showing here. We have been basically we have been in the process of combining our Tully-Fisher distances with the other methods in order to construct the Cosmicflows-4 distances. And uh, Kulan, Howlett, and Khaled Say told us they've been collaborating with us on the project. They told that they have been looking at their own sample, they have been working on the fundamental plane distances. They discovered a bias in their sample, and they discovered the same bias in our sample too. When they plotted the Hubble constant against the R absolute apparent magnitude, they discovered that the distances for fainter galaxies are larger than the other distances, because the Hubble constant is going down. And once I looked at all of those plots again, I discovered the same bias. Here I am showing W1 band, and you see that the Hubble constant goes down, and it means that something is wrong. And it took us about 4 or 5 months to just find the source of this bias. And the source of this bias comes from the fact that the TF relationship is not a linear relationship. It's linear as long as you are working with very bright galaxies, the galaxies with very large line widths, large galaxies, or bright galaxies here in this region. If you fit a line in this region, you end up with a line that is more or less like this green dotted line. But here in this region, you see that there is a curvature and points are going down. So you end up with measuring the distances that are associated to this fiducial relationship, which is larger than the distances that these galaxies are actually at. That's the reason that the Hubble constant falls down here. You can address that problem in several ways. One of the ways is to just feed two lines and break the line at the center here at about 2.5, 2.4, 2.5. Or you can use a curve relationship, or you can use any other machine learning or Gaussian process or any other data-driven methodology that you want. But the thing is that none of these methods are backed with physics, and we want some physics to be involved. And the reason that these relationships are kind of different, you see that curvature here, is because we are looking at the stellar mass of the galaxies here, because we are using luminosity of the galaxies here, and we are dealing with the luminous matter of the galaxies. But we know that in this region where galaxies are smaller, another component becomes important, and that component is the mass of the gas that comes from atomic hydrogen and helium. So therefore, we add the gas mass to the stellar mass, and gamma here is the mass to light ratio, L is light, M is the H1 21 centimeter mass, and 1.33 is to we just multiply that hydrogen mass by this factor to just compensate for the helium mass. We add these two components and we end up with the baryonic mass of these galaxies, and we construct another relationship that uses the baryonic mass as opposed to the absolute magnitude of these galaxies. And here I'm using 75 because this is just a basic calculations back of the back on the envelope calculations, where I am assuming that Hubble constant is 75, and I constructed distances, rough distances of these galaxies to just study the phenomenon here. As you see, when you add gas and a star, I should drop an S here. When you add gas and a star, gas and a stellar mass here, you end up with a linear relationship which works much better than the relationship that you had earlier. What I do basically here is the mass to light ratio is not constant for all of these galaxies, and it's a linear function of color. So that color can comes from optical G minus I or W1 minus W2, and I fit for 0 point a slope these parameters alpha and beta all together. I fit all of these parameters together in order to minimize the scatter about the fitted relationship. I know that if the scatter is minimized, I end up with good distances. And also when I minimized all of these, I optimized my fitting process. That's a Bayesian framework. When I plot the fitted lines here and I compare my plots with the literature, I see that my plots actually look very good. Here people using different methodologies, different physics and different mechanism to derive their mass to light ratios as a function of color, but I'm using only Tully-Fisher relationship or Byronic Tully-Fisher relationship to construct that relationship. And we see that that method works, and hopefully that gives us a best good result. So we have, this is the endpoint of the fitted lines. Like we have here the fitted Byronic Tully-Fisher relationship, totally linear. The diamonds here, like the green diamonds, stars and circles or dots here, show different calibrators, 0 point calibrators, Cepheids calibrators, TRGB calibrators, and the other calibrators. If I have two calibrators for the same galaxy, I just average them out. And at different bands, optical bands, RI and Z bands, I average them out, and I use an average relationship for optical and another relationship for infrared, because for some of these galaxies I have optical data, and for some of the other galaxies I don't have optical data, I only have infrared data. Once I have this relationship with slopes and 0 points, I can construct all of these distances. These distances should be compared with the other distances we have. For example, I compare the distances I've got with those from Cosmicflows-3 to make sure that I don't have any other biases versus redshift. And the difference is not that significant, and I can claim that the new distances are better than previous distances that I had. They don't have any bias, even if I construct, I don't have it here, but if I construct the relationship between um, Hubble constant and magnitude, apparent magnitude, there is no other bias as well, because that relationship is better than the previous one. So basically for Cosmicflows-4, we are going to use Byronic Tully-Fisher distances as opposed to Tully-Fisher distances because they are better They are more accurate. They don't have any bias. As soon as we have this work published, we can just go on and come up with the Cosmicflows-4 catalog that has 50,000 galaxies, and it's gonna happen in early 2022. And thank you very much for having me again and for giving me the opportunity to talk about my research.